Alright, silly people, here's the situation. We're in the harmonic oscillator, and we're doing time-dependent perturbation theory, um, where we're going to be calculating the probability that the harmonic oscillator is going to go from the ground state to the first excited state, given this perturbation in time there. And first thing I'm going to do is I'm actually going to rewrite it so it's not so obnoxious. Like that. And then on the bottom we'll have tau squared plus t squared. And then Shankar pretty much lines out a process to do this in the section preceding this problem. We calculate this constant d uh, as a function of time, which is just representative of like how much this particular wave function will contribute to the total wave function at time t. Uh, like as a function of the constant and the eigenstates of the problem. Um, so what you want to do is you want to look at the constant dn, so for any arbitrary eigenstate at time infinity, which using this formula is looking like dn0. We got minus I over h bar. We got the, instead of having the bottom bound be 0, you have it be minus infinity, because it helps with the integrals. And then the f0 that we're looking for is now just eigenstate n. And then we have the perturbed Hamiltonian, and then we're looking for the chance that it will transition from the ground state to any other state. So the initial will be 0. And then we have the omega fi. In this case, is just n omega t prime, and then this is dt prime. And then this Kronecker delta I'm going to have go to 0 because we just said that n is supposed to not be 0. So that goes away. We can start plugging in our perturbed Hamiltonian. We'll have minus I over h bar. We're multiplying it by a minus tau squared e fancy e over tau squared plus t squared. And I had to leave the x inside because that's actually the position operator. We need to calculate that expectation value, the matrix element, I guess. This is n omega t prime, this is d t prime. And actually, I made a mistake. You can't pull this out just yet. That denominator needs to stick around inside the integral because this is a time integral. So we'll have e to the I n omega t prime over tau squared plus t prime squared dt prime. Right. So there's a substitution that we're going to make for the position operator. Something that you can do with specifically the harmonic oscillator, is that you can change over the position and momentum operators into combinations of the raising and lowering operators, which Shankar writes here, where A is the lowering and A dagger is the raising. So we'll just apply that here. We'll simplify the prefactor a bit, so we'll have tau squared e fancy e times I over h bar of square root h bar over 2m omega. And then inside of this integral, we'll have n with a and a dagger with 0, and then we'll have this stuff again. And this is t prime. This is tau squared plus t prime squared dt prime. So we have to operate the lowering and raising operators on ket 0, the ground state. The result of operating the lowering operator on it is 0, because it can't go any lower. The raising operator is just going to raise it to state 1 with a 1 tied to it. So this turns into, let me write my fancy E again. H bar, we got the root h bar over 2m omega. We got the integral. It's n1. And then that overlap is going to give us a Kronecker delta, right? So we'll quickly rewrite that the result of the inner product of eigenstate n with eigenstate 1 is a just a Kronecker delta n1. So that means that the probability that the transition will be from the ground states to any state except 1 will be 0. Or I mean the constant is, and by proxy the probability is also 0. So the only thing we can really calculate is d1 then, not dm. But that's all we need anyway. So just plugging in a 1 everywhere that there's an n, there's only really one place that's in there. We'll have in the integral, it's e to the I omega t prime over tau squared plus t prime squared dt prime. Now, this is a contour integral. I don't know how to do contour integrals. As much as I like to actually do integrals in the most analytic methods as I can on this channel, I have no idea how to do this, so I looked it up. And I'll show you what I got. Writing all this stuff out again. I over h bar root h bar over 2m omega. This integral turns into pi over tau times e to the minus omega tau. Thank you, ChatGPT, for that one. So simplifying that, we'll have tau squared, or not tau squared anymore, just tau. Pi tau e fancy e I over h bar root h over 2m omega e to the minus omega tau. And then to find the probability that the ground state transitions into the first excited state, we're going to square this result, the square modulus of that result specifically. And that's going to look like pi squared tau squared e squared, fancy e squared, over h bar squared times h over 2m omega times e to the minus 2 omega tau, and we'll simplify it further. So we have pi squared tau squared e squared fancy e squared just over 2m omega h bar, and then we'll have e to the minus 2 omega t, not t, tau. And I think that is what Shankar got, so we're looking good there. All right.